Okay, so in this particular lecture, we are going to talk about direct products. Okay, direct products, and this topic is very essential under group theory. Under group theory, the topic can be extended as well to the other algebras like rings, vector spaces, modules. But we start the topic, or rather, we start the discussion on direct products through group theory. Okay. Um, Direct product is basically a step for constructing arbitrary groups from known groups. Okay, that is the you know the the significance of direct products, you might say. Okay, when you are given a certain group, you try to construct new groups out of the known groups. Got it? Yeah. We know how to construct new groups using a given group and one of its automorphisms. We will discuss these things in some other lecture, but there are ways to construct a new group from a given group and its automorphism. And a special case of this type of construction is what we have seen in dihedral groups as well. Um, so we intuitively have an idea that there are ways to construct new groups out of old groups. So this is one of the most dedicated ways to do so. Okay. Now we start our discussion by using two known groups, and when we completely understand the concept using two known groups, it will be very easily understandable for a finitely many groups. Okay. Okay. So let's start. Okay. So before moving on to the direct concepts of direct products, let us first understand, or rather let us first recall what are the Cartesian product of two sets. Let's say, so let A and B be two sets. Okay, we define the Cartesian product of A and B to be the set of ordered pairs of elements from A and B respectively. Okay, so we define it like this. So A cross B is defined to be this set of ordered pairs AB such that A belongs to capital A and B belongs to capital B. Okay, got it? Yeah. Now suppose we do the same for two groups. Okay, so suppose G1 and G2 are two groups, and let G be the Cartesian product of G1 and G2. Okay, now we claim G is a group under preservation of operation of G1 and G2. Okay, so what do you mean by it? Let us understand it. Okay, So let's say G1 G1 is an additive group. I mean the symbol used is addition, and let's say G2 is a multiplicative group. Okay. Then choose two ordered pairs, let's say AB and CD from G, which is for the time being the Cartesian product of G1 and G2. Then the operation defined on G, let us signify it with this symbol. It is simply the composition of the elements respectively according to the operation of the group they are in. Okay, so it is A plus C and B dot D. Got it? This is what I mean by under preservation of operation. Clear? Because A and C are elements from G1 and G1 is an additive group. B and D are elements from G2 and G2 is a multiplicative group. Clear? Okay. But when we will be studying these things, we are more generally gonna opt for multiplicative operations. And conventionally we treat every group to be a multiplicative group, regardless of not talking about any specific operation. Okay. So we define G, rather we claim that G dot is a group where for all ordered pairs in G, their composition is simply defined as the composition of the respective elements according to their coordinates. Okay, rather according to their position in the ordered pair. Got it? Yeah. Now see, closure is trivially achieved, right? Closure is trivially achieved. Yeah, so closure is trivially achieved, right? Because you can directly see from the definition of operation that AC is an element of G1 and BD is an element of G2, because they are individual elements from G1 and G2, and G1, G2 being groups, they have the closure property in them. Associativity is also very evidently seen because we just treat each component as an element of the respective groups, and so each component obeys associativity, so the ordered pair holds associativity as well. You can check it on your own. If we talk about existence of identity, then it's also very evident. Just take the ordered pair E and let's say EG1 and EG2. Okay, where EG1 is the identity element of G1 and EG2 is the identity element of G2. Then if you compose this with AB being an arbitrary element from G1 cross G2, then what do we get? So EG1 dot A, which is A itself, and EG2 dot B, which is B itself, right? And if you do it same for the other side round, you get the same result. Okay, yeah. So thus we have an identity element, and it's obviously unique because EG1 and EG2 are unique identity elements from G1 and G2 respectively. So the ordered pair formed by those two identity elements also form an unique element in G. Okay, and in a similar fashion we can also see for the existence of inverses, right? Because if you choose an ordered pair from G, then the ordered pair A inverse B inverse serves as the inverse element for AB. Correct? Got it? Yeah. So no doubt G forms a group as well, and again under preservation of operation. Okay, but we are not concerned about the operations anymore. We just generally write it in terms of multiplicative operation. So is it clear? Got it? Okay. Now forming a group using the Cartesian product of two groups is what we term as the external direct product. of the two individual groups. Okay, so we define G A let me write it as or rather let me write it like this. Definition: let G1 and G2 be two groups, then the external direct product of G1 and G2 is the group G, which is defined as G1 cross G2. Got it? This is what we call the external direct product. Okay. Now this is very much clear that if we know the structures of A and B, then the structure of G will be heavily reflected. Sorry, the structure of A and B would reflect heavily on G, right? Because G is indeed constructed from A and B, right? Okay. Now we need to check a few things before moving on to what we call internal direct product. The term will be pretty much clear to you as we reach it. First, notice something. Let us consider this set A bar, which is A say AEB, okay, or let me write out using the symbol I have already used. Say G1 bar, it is the set of elements G1 EG2, okay, such that G1 belongs to G1, small g1 belongs to capital G1, okay, and obviously this is an element of capital G, right? Now this is obviously a subset of capital G, right, which is equals to G1 cross G2, clear? And where EG2 is the identity element of G2, okay. Now notice that A bar is a subgroup of G. A bar is a subgroup of G. You can prove it very trivially, okay. A bar is a subgroup of G. Moreover, so this is point number 1. Point number 2 is A bar is isomorphic to A. A bar is isomorphic to A. Now how is it so? You just take a mapping. You just take a mapping phi from A to A bar such that any element, sorry, I am again using the wrong symbols. One second. Okay, so I have written the symbols as G1, so G1 bar, and here you have G1 bar isomorphic to G1. Correct. Yeah, my bad. Okay. Yeah. So take the mapping phi from G1 to G1 bar such that any element G1 from capital G1 gets mapped to G1 comma EG2. Okay, got it? And this is pretty trivially an isomorphism. Got it? Clear? Yeah, you can check it on your own. It is very easy to check it. Clear? One more thing to notice here is that G1 bar is normal in G as well. G1 bar is normal in G as well. Notice, consider the element say G1 EG2 from G1 bar and take AB from G. then AB times G1 EG2 times AB inverse, what will it be? So it is AB G1 EG2 times A inverse B inverse, and by associativity we can compose them all together. So this is A G1 A inverse, and here you have B EG2 B inverse, which is A G1 A inverse, and this is EG2 itself, right? So this obviously belongs to G1 bar, correct? Yeah. So G1 comes out to be normal in G. Is it clear? Okay. So what all we get from here? Just summarize it. So we get A bar to be an isomorphic copy of A, which is in G, and which is normal in G, right? Which is normal in G. Now in a similar fashion we can also do the same thing for the set B, right? For the set, okay, I am using again the wrong symbols, pardon me. G bar, yeah, copy of G, G1, yeah, okay, yeah, okay. So yeah, now we can do the same thing again for the group G2 as well, right? We can do the same for the group G2 as well, right? By constructing G2 bar as EG1 and small g2 such that small g2 is in capital G2, correct? And this will obey each and every result we have got for G1 bar, right? Right. So this part is done. Now we claim that G can be written as G1 bar G2 bar, right? I think you people already know about this product form, product of two sets, right? Two groups in this case, okay, where every element you take from G, it is the product of two elements individually, one taken from G1 bar and one taken from G2 bar, okay. So we claim that G equals to G1 bar G2 bar, and every small g in G has a unique decomposition in the form G equals to small g1 bar small g2 bar, where g1 comes from g1 bar comes from capital G1 bar, and g2 bar comes from capital G2 bar, with g1 bar from capital G1 bar and g2 bar from capital G2 bar, correct? Now let's check how is it true. So let AB from G, then AB can be written as AEG2 times EG1B, right? And where AEG2 is obviously belongs to G1 bar, and EG1B, this belongs to G2 bar, correct? So considering G1 bar, small g1 bar to be AEG2 and G2 bar to be EG1B gives us the decomposition, but we have not yet proved that it's unique. So gives us the decomposition. Now we need to check whether it's unique or not. So let there exist xy, rather x bar y bar in G1 bar and G2 bar respectively, such that AB is equals to x bar y bar. So from here what we get? So from here we get that AB, which is already A bar B bar, we're writing it as x bar y bar, and note that this x bar y bar can be actually be taken as x eg2 and y bar can be taken as eg1y by the same steps we had obeyed in this case. Okay, so this is equal to AB, and what is this? This is nothing but xy, right? This is nothing but xy. So from here what we get? A equals to x and B equals to y by comparing of components. So that's unique, right? Therefore the decomposition is unique. Yeah, clear, right? Now this is what we call an internal product. Okay, this is what we call an internal product. Okay, this decomposition of G into normal subgroups of itself isomorphic respectively to G1 and G2, where G is the external direct product of G1 and G2, is what we call the internal product of G1 bar and G2 bar. We already know what G1 bar and G2 bar is. Clear? Got it? Okay. Now with what all we have learned, now we can obviously extend this concept to any n groups. Okay. So generalizing the facts learned for two groups, we have, so let me define it. Let G1, G2 till Gn be any n groups. Let G to be the Cartesian product of each of the n groups. Okay, we define a product on G via, so n tuples in G via another set of n tuples in G. They simply have the product coordinate wise. Okay, so G1 G1 prime, G2 G2 prime, and so on till Gn Gn prime. Okay, Now you can obviously see that this product obeys every rule of being a group. This G is called the external direct product of G1, G2 till Gn, right? Okay, and let Gi bar be defined as the set of n tuples E1, E2 till Ei minus 1, Gi, Ei plus 1 till En, where Gi belongs to capital Gi. Okay, then Gi bar is normal in G, Gi bar is isomorphic to capital Gi, and G is equals to G1 bar, G2 bar till Gn bar is called the internal product of G1 bar till Gn bar, or rather you can say them to be the internal product of G1 to Gn as well. Okay, because they are isomorphic copies. Clear? Got it? Got it? Okay. Okay. Clear. So this is the case. Okay. Now let us take an example. Let us first write one more definition. One second. Yeah, so let us write one more definition which goes on like this. Let G be a group and n1 n2 till n small n be normal subgroups of G such that G is equals to n1 n2 till n small n, and number 2, given an element of capital G, then G can be decomposed into small n1, small n2 till, okay, let me write it as small m. So small m1, small m2 till small mn, where mi belongs to capital Ni, and this representation is unique. Clear? Clear? We say G is the internal direct product. We say G is the internal direct product of n1 till n. Okay? Clear? Let us take an example. Let G be a finite abelian group. Let G be a finite abelian group. Finite abelian group of, say, order p1 to the power a1 till pn to the power an, where p1 till pn are distinct primes. Then let p1 be defined as the p1 silo subgroup of G, rather let pi be defined as the pi silo subgroup of G, and if you know the silo theorems, you can notice that pi will be normal in G. Okay, because pi will be a unique pi silo subgroup of G. Clear? Then G is the internal direct product of p1 p2 till pn. Clear? Now we come to a very important case. So consider G to be an internal direct product of n normal subgroups. Okay, consider G to be internal direct product of n normal subgroups. I am writing it here to be internal direct product. Clear? And let T to be the external direct product of these normal groups. Now in this case we are considering each ni to be a normal subgroup of G, and in the second case we are considering each ni to be simply a group. Okay, then obviously T will be an external direct product of each of the groups ni, and G is an internal direct product of the normal subgroups ni. Got it? Now our goal is to show that G is isomorphic to T. Okay, because if we are successfully able to show this, then we can obviously abolish the terms, the prefixes external and internal when studying direct products. Because if the external direct product of certain groups is isomorphic to the internal direct products of those groups which are normal subgroups of some other group G, and they're isomorphic, then we no need to talk about direct products in terms of external, in terms of being external or internal, because they will be the same groups up to isomorphism, right? So that is what we need to do, and then we can obviously talk about simply direct products. Got it? Because direct product is actually very important in learning finite abelian groups. That is actually why we need to study direct products. Okay, so first a lemma. Suppose G is the internal direct product of n1 n2 till say nn, then for all I not equals to j, ni intersection nj is only the identity element, and if we choose an element A from ni and an element B from nj, where obviously I is not equal to j, then the two elements commute. Okay, this is what we need to show. Okay, so let's see the proof. So let X be an element from ni nj, where I is not equal to j. We need to show that X is nothing but E, identity element of G. Okay. Now notice. Now since x belongs to ni intersection nj, that means x belongs to ni and x belongs to nj. Then x can be written as e1 till ei minus 1 x ei plus 1, we have ej, and here we have en, right? I think you people have understood how I have decomposed x into a form of products of the elements of n1 n2 till nn. Okay, and so this is because since x belongs to ni, and x can be also decomposed as e1 till ei minus 1 ei plus 1. So in place of ej, here what we have, x, right? ej plus 1, and here we have en, because x belongs to nj as well. Clear? Clear? Okay. Now we have already shown that the decomposition of an element is unique, right? Right? What I am trying to say is that x has a unique representation. X has a unique representation in the form m1 m2 till mn, where mi belongs to ni for all I equals to 1 to n, right? So x must coincide from the two representations of x which we have written here, right? So from here what we get, so therefore x must be equals to ei and x must be equals to ej. But notice something, that this ei and ej are nothing but the identity element of G itself, which is E. Obviously, right? Because G is an internal direct product of each Ni. Clear? Clear? Right. Now we can say it like this, but Et is nothing but E, right? For all t equals to 1 to n. Because these are normal subgroups of G itself. Each Ni is a normal subgroup of G itself, right? So each Et is nothing but the identity element of E. Got it? So from here what we say? So from here we got x is nothing but E, which implies Ni intersection Nj is E. Clear? Clear? Now we take the next part. Okay. Now suppose let's say A belongs to N1, let A belong to Ni, B belongs to Nj, and I is obviously not equals to J. Since Nj is normal in G and A belongs to Ni, means A belongs to G itself, we can say that A, B, A inverse, this is an element of Nj because it's normal. Clear? Now since B belongs to Nj and Nj is a subgroup of G, B inverse is also in Nj, right? So from here by the closure we get A, B, A inverse, B inverse also belongs to Nj, which implies A, B, A inverse, B inverse belongs to Nj. I am removing the brackets. Clear? Clear? Now in a similar way we do the same thing for Ni, because A, we have taken A to be in Ni, so that implies A inverse is also in Ni, right? So that means, and B is in Nj, and that means B is in G itself, so that means B, A inverse, B inverse belongs to Ni, since Ni is normal in G, right? And since A is in Ni, we can say by closure that A, B, A inverse, B inverse is in Ni. Rather A, B, A inverse, B inverse is in Ni. Now this element is in Ni and this element is also in Nj. So that means A, B, A inverse, B inverse is in Ni intersection Nj. And we have proved that Ni intersection Nj is nothing but identity. So that means A, B, A inverse, B inverse is nothing but identity. And that means AB is equals to BA. Clear? Okay. So we have proved it. Got it? Okay. So now we come to the desired isomorphism between the external and the internal direct product. So we state it as the theorem. The theorem is, let G be a group and suppose G is the internal direct product of N1 till Nn. Let T be the external direct products of N1 till Nn. Then G is isomorphic to T. That is what we need to prove now. Okay. Define phi from T to G such that phi of M1, M2 till Mn is equals to M1, M2 till Mn. Clear? Clear? Now notice that phi is certainly onto, right? Phi is certainly onto, as you know, as if x belongs to G, let's say, then x can be written as some A1, A2 till An, where each Ai belongs to capital Ni. Then phi of A1, A2 till An is nothing but A1, A2 till An, which is nothing but x, right? So for all x in G, we have a set of elements. We have its pre-image in T, right? So which implies phi is onto. 1 is also a direct result of the representation, or the representation of decomposition being unique, right? This is also pretty clear. That is, since the decomposition of elements of an internal direct product is unique. So 1 holds as well. 1 property, let's say, holds as well. You can check it on your own. It is pretty easy to notice now, because if you have understood the uniqueness of decomposition, then 1 property is very, very evidently seen from there. Clear? Now let us check about the homomorphism, because that is the only thing left to see. So let say x be A1 till An, y be B1 to Bn, and what is phi of xy? So phi of xy is phi of A1, A2 till An as an n tuple, and here we have B1 till Bn as another n tuple. Coordinate wise product gives it to be A1 B1 till An Bn, and the mapping of this will come out in the form A1 B1, A2 B2 till this is of the form Bn minus 1 An Bn. Now by associativity you can write it as A1 B1 A2, then here you have B2 A3, no comma here, sorry, and so on. till bn minus 1 an, and here you have bn. Now notice, since 1 2 2 3 are the the notations of the elements inside the brackets, they commute, because we have already seen that two elements taken from ni and nj, where I is not equal to j, they commute. So this is simply a1 a2. So here we have b1, a3 comes here, a3, b2 goes there, and here you have so on and so forth. Here you have again one commute, here you have bn minus 1 and here you have bn, and if you continue in the similar process, because then you group these two elements, you commute them, you will get it to be a1 a2 a3 till an, you have b1 till bn. And what is this? This is nothing but phi of a1 till an, phi of b1 till bn, which is phi of x, phi of phi. Hence phi is an isomorphism, right? Which implies also trivially that G is isomorphic to T. Clear? Clear? Okay. So external product of a certain of certain groups Gi is same as the internal product of their bars, is actually what we have, because what we have actually seen here is that, see, if G is isomorphic to the external direct products of Gi, then G is the internal direct product of Gi bar isomorphic to Gi, right? So G, so what we so we simply say, G is the direct product, no need to mention external or internal, right? Direct product of Gi or Gi bar. Got it? Clear? Now eventually, as we study vector spaces, rings and modules, we will see that this theory extends to the other algebras, right? Vector spaces, rings, modules and so on. Got it? And this is very important in understanding the finite abelian groups. So let this lecture be up till this much, guys. In the next lecture we will be trying to take some more important topics on abstract algebra. So meet you guys in the next lecture.